Hi, I'm Jack Terrell. I am one of the RLAs from Will Rice College, and I'm, due to this weather and lecture being canceled both days this week, I'm making this sort of lecture replacement video. I'm gonna start out basically by explaining what bisection is, and I'm going to do that through an example where we'll try and determine what time of day exactly Braised Bayou flooded over the Main Street Bridge. So, what we can basically, our sort of problem setup that we have is we have this sort of function of time, right? Some like height as a function of time. That's just going to be equal to height of Bayou over the bridge. Okay? And then we have some time interval where we know it wasn't flooding to start with, and we know it was flooding at the end. So we have some time interval, and let's just say that time interval was sometime yesterday. So let's say it was from 0 hours to 24 hours. So sometime between 12 a.m. and 12 a.m. the next day. All right, so the way that we're going to solve this problem, is we're not just going to look at all the pictures. Like say you're, on the online flood camera website, look at all the pictures all day for the bayou, simply because that's a lot of pictures to look at. You might have started looking at, the 12 a.m. pictures. You go through that and look at one every 5 minutes. By 1 a.m. you've already looked at 13 pictures and you're really bored, so you might skip ahead. But if you were coding this in MATLAB wouldn't necessarily skip ahead. So it would end up being really inefficient because you're looking at a lot of pictures where it's not even close to flooding, and you just generally have to look at a lot. So the other way, and the way the bisection algorithm works, which is the algorithm we'll be working with this week, is we start looking at the two ends of the curve, which is the height of the bayou over time, and we essentially start cutting that interval in half, look at the midpoint, and see whether or not it was flooding at that time. So let's do that. So I am going to start out by asking, is it flooding at, let's try 0, t equals 0, i.e. 12 a.m. And you get no. So I get somehow negative. Let's try t equals 12, or t equals 24, which is 12 a.m. the next day. And it is. So if we know these two things, what we know is that at some point, the answer, if we chose some time between t equals 0 and t equals 24, the answer changes from no to yes. And we're trying to find that time. We also might know the height at that particular time. And that would be how we'd know whether or not it's flooding, right? Because we have this function h of t. That's the height above the bridge at the time. So it goes from negative to positive, right? So the bisection method, and before I go to full algorithm talk, what I'm going to do is actually start out just by explaining it with some curve. And this isn't some curve that MATLAB will know. You only can ever really evaluate to know points of this curve, right? Because if we knew the shape of the entire curve, that would require knowing all the points on it. And depending on how hard, knowing the height at a certain time or looking it up is, or how time intensive it is, getting that curve would be sort of difficult. But let's say that this somehow is some true curve that we knew, where between 0 and 24, we know that it did flood at some point. Alright, so let's apply bisection. So what bisection tells us to do is it tells us to keep cutting in half until we reach an interval where the actual height above or below, flooding is not really that noticeable. Like until it's within some tolerance, some change of distance. So let's first ask the question, is it flooding at t equals 12 or noon? And we, pull up the picture, we look at it, and at t equals 12, we get the answer that it's not. So no. So what can we infer about when the flood time happened based off of knowing it wasn't flooding at 0, it was flooding at 12, or it wasn't flooding at 12, and it wasn't flooding at 24, or it was flooding at 24. What can we infer? We can infer that because there is the sign change, because it went from negative to positive on this half of the interval, that the actual 0, the time it flooded, is on this half of the interval. So we can throw this area out. We don't have to know about it anymore, and we can refine our search to between 12 p.m. and 12 a.m. the next day. So let's try another midpoint. So the midpoint between 12 and 24 is 18. So let's ask ourselves, is it flooding at t equals 18? All right, and we draw it here, 18. And you can notice that this isn't exactly where it crosses the x-axis. So at 6 p.m. and we find that it is. Okay? And we ask ourselves, okay, is 6 p.m., is the distance it is from flooding on either side, is that precise enough for us? And if it is, then we stop, and our answer is 6 p.m., right? If it's not, then we'll keep on using midpoints. So we know that it, over this interval is the interval we're now considering the possibility of flooding. We know it actually wasn't flooding at noon, it was flooding at 6, and it was flooding at midnight. So the actual sign change where it went from not flooding to flooding was between noon and 6 p.m. So we can throw out the 6 to midnight interval and keep on looking in here from noon to 6 p.m. We then choose a midpoint, which would be t equals 15 or 3 p.m. And we look at the picture and we determine no, it wasn't flooding. Or that the value of the height function is negative. So we then know that the sign change, or the time it started flooding, was between 3 and 6 p.m. And we could try, t equals 16.5 or 4:30 p.m. And we'll see maybe it's not flooding. And we'll keep on going until we eventually reach some time that we find a number for, where the difference from that actual flooding height is going to be smaller than some value that we set at the beginning. And that value is called tolerance, or a Y tolerance, or tall as we call it in here. So you might say tall is 2 inches. So if it's within 2 inches of flooding, or it's flooding by only 2 inches, we consider that close enough and consider a time point where it's within 2 inches of the threshold of flooding to be acceptable. So that would be how you would use bisection in this case. So I'm going to start sort of talking about where this might break down, and talking about what we'll do with the lab. Because this isn't something you can really program in MATLAB yet. You don't have some formal way to talk about it. You don't have it in code speak, like for loops and while loops and ifs and things like that. So let's look at this a little more formally. So assuming we have this function, and it does something like this. It doesn't necessarily have to go negative to positive. It can also go positive to negative. We have this interval, right? Let's say this is the interval. In the code it calls it A to B. Okay, we can see that it's positive here, negative here. So it's really clear to us that this function has exactly one place where it crosses 0 between A and B, right? But, that's actually not guaranteed. Now the way we would find this, and let's call this x, and let's call this f of x. The way we would find whether or not it is going to have a crossing is if f of A times f of B is less than 0. So this is true if and only if f of A is greater than 0 and f of B is less than 0, or f of A is less than 0 and f of B is greater than 0. i.e., it's true if and only if it is a sign change between the two ends of our interval. Right? So that's the way we'll check in. And your code, if it checks that and finds that to be false, then it should display some sort of an error message. But let's think a little more about maybe the bayou example. And let's suppose that the bayou flooded and then the water receded, say there wasn't any more rain for a little while, and then it flooded again. So something like this. So flood, water recedes, floods again. Knowing this is knowing that it did go from flooding to, or not flooding to flooding was, it does guarantee that there's a time where it started to flood somewhere in here. But what it doesn't guarantee is that there is exactly one of those. Because it actually starts to flood, or is right at the threshold of flooding, and then it stops, so it reaches that 0 again, and then it starts again. So there's no real way you can check this without looking at the whole curve or doing some pure mathematics on it, without evaluating, using theorems and stuff. But checking the first derivative, and so this will actually guarantee at least one sign change, but it won't guarantee only one sign change. That's sort of a weakness. So if you chose a more appropriate interval, say this was actually the point you were interested in, you chose this interval as your B, then you would have only one sign change, and you'd find just that 0 right there. But it's really hard to actually determine that, and finding an analytical bound is somewhat difficult. But fortunately for the function that we're doing, there actually is a way you can use a little bit of math to determine an analytical boundary. Some A and B where there's always at least 1 0, or the 0 we're looking for, and exactly 1 0. So yeah, just that as a note. So if it floods, stops flooding, and then floods again, you can have kind of messy stuff. So let's talk about the bisection algorithm a little more. And this is called an algorithm because, well, an algorithm is a series of steps that you would use to solve a problem. So what we can do is, just write the bisection algorithm. So I'm going to sort of set this up. So we have some function f. F of x, okay, and it is continuous on the interval a to b, and this close brackets and then a comma b in mathematics speak means a interval, or like a whole continuation of the real number from this lower number all the way up to this higher number. So this just means a portion of the number line. It is continuous. All right, and we have that We have some tolerance. Tall. Let's call it tall. Where we want to find x such that the absolute value of f of x is less than tall. Okay? And then we have our initial x values of a and b. Okay, so with all this knowledge, this will allow us to run bisection. So what we're basically going to do is, and this is sort of something called an iterative improvement algorithm. You start with some guess, and if it's not good enough, then you improve the guess and keep on going until it is eventually good enough. So the way that Steve Cox wrote this, the old professor, was that you should basically start out by testing if there is actually a sign change. So remember from the last example, check basically if f of a times f of b is less than 0, then we can proceed. Otherwise, basically, our code will break down, and you'll want to say like, else display error, some sort of error. Okay, then within here, I'm not going to number these steps. Within here, you basically can just look at, how we will improve a and b. Right? So we have some initial x, some value of x, and this isn't this final x, but when we're done, this x will be our final x. The first thing you're going to want to do is set x is equal to a plus b over 2, or basically the midpoint of the interval. So like remember, I went the time halfway through the times that we're looking through. Okay? And then once you have that midpoint, you're then going to test if at that midpoint the function is smaller than tolerance. So you're going to check if it is smaller than the tolerance, then if smaller than the tolerance, then or if it is bigger than the tolerance, right? If the absolute value of f of x is greater than the tolerance, then basically keep going. Through like different improvements. And what this sort of if this then keep repeating this type of thing is called is a while loop. So we talked about for loops already, where you are doing some set of code for every element in a vector. This is something called a while loop, where you're instead doing a set of code while a condition is true. So it's like if this is true, then keep repeating this. So when I said if there, I really meant while. So while the absolute value of f of x is greater than tolerance, then basically keep going or get an improved x, right? And then I'm just going to close out that while. And the way that you'll get the improved x is basically, if basically the difference or the sign changes on the left side, you're going to save the left side and keep looking for it on the left side. And otherwise, if the sign change is on the right side, you'll keep looking for x on the right side. So there's sort of a lot more that needs to be written here, so I'm going to have to move this down. But basically, this section of code can be summarized as cut interval in half by changing A or B. And you also need to redefine x too. Somewhere in here. And so after you've cut the interval in half, you've redefined x at its midpoint, right? Because it's just equal to a plus b over 2. And if you never do that, then you'll basically be keeping the same x, and this truth of this statement will never change. But the way that you'll cut the interval in half by changing a or b, so that it's the half containing the sign change, is sort of this other set of code that will be more along the lines of an if statement. So what you do in here is you would instead, let me get this, try this blue marker. You would instead use this little piece of code that will basically say, you know, if change is on left half, then basically replace x, or replace your lower bound. So like here, let me sort of draw this. You know, you have the interval where a is on the left half and b is on the right half, and x is in the middle, right? And if the change is on the left half, then you want your new interval to be from here to here. So the a stays the same, right? And the interval in the next iteration will have this x basically be, or the b be the old value of x. It's like the new upper boundary was the old midpoint. So the value of a didn't change from cutting it in half, but the value of b is changed to the old value of x because the old value of x was the midpoint. And that's the definition of what the left half of the interval is. So you just do b is set to the value of x, and otherwise that means that the change is on the right half, so a is set to the value of x, right? Because if you're cutting it in half this side, b stays the same, and the left boundary will now be the old midpoint, which is x. And that's sort of what you would do. Now how would you test if change is in the left half? Well, you'd keep on using something like this. But instead of these two interval boundaries, which are asking is there change on the whole interval, seeing if there's change in the left half of the interval would basically be using f of a and f of x, right? So by change I mean sign change too. So if f of a times f of x is less than 0, then set b to x. Otherwise, set a to x, and then you end. And you'll basically, yeah, this is the entire bisection algorithm. Of course, if you're coding this in MATLAB, you'd need an end to close out this else. And yeah, so this isn't MATLAB code whatsoever. Many of the variable names and many of the words will still be preserved, but I think that this sort of code is already provided to you. If you click on the biscale.m, which there's something about that saved in the PDF, but I can't find it. So maybe they stopped giving that to you. But anyways, look at biscal.m. The function that you're going to be doing, instead of being f of x, it'll be coolfun of x comma L. So just everywhere you write, so some f of some variable, I'm just going to call this variable k, is equal to coolfun of k comma L. Where L is some constant that is defined up before this algorithm is ever run. And this algorithm will live in your function called cool. There will be some code before it, and there will also probably be some code after it to process the results. So that's it for sort of the theory of bisection. And then I'll move on to sort of our practice and what each function is going to entail, so you can start working on the code as soon as possible. Okay, bye.